I'm now in the third simulation, which is the Falstead simulation, but I'm going to kind of stay down here looking here. I have put it on the harmonic oscillator, so that's important. And I really encourage you, before you get started with this, to hopefully play around a little bit and understand what you're seeing. So this top section here, there's kind of 4 parts on the screen. This top section, each line is one of the energy eigenstates, and you can see your potential here. You can in fact go through and change your spring constant, which changes your potential. You can change your particle mass, which changes your energy states, and so on. The offset isn't particularly important. That shifts it back and forth. Resolution makes your computer more or less happy, kind of so does the simulation speed, but that might make you more or less unhappy. So this first one, we see the energy eigenstates, we can select them. Now notice that when I mouse over, and I can't mouse both places at once, you see your wave function in that second window. So the only time you see the wave function is when you're actually selecting an energy eigenstate. When you're not mouse overing it, what you're actually seeing here is your position probability distribution. And the color is giving you effectively the kind of a phase, right? So if we think through what our wave function was looking like, we can think about this as being, okay, you would be, let me get on the one I'm actually on, squaring it. And so the blue represents where it's actually where a wave function is positive, the yellow represents where a wave function is negative. So now what's this lower window? This is actually our momentum distribution. And as we mouse over different spots in the momentum distribution, you actually see your wave function changing. So I can pick one of these, and this would give me kind of a momentum Gaussian. And notice that right now my mouse is for create Gaussian. So let's go back to the ground state. Now then the fourth one is these circles. And the circles are great because this actually is what allows you to make a superposition by hand. And so if we let the simulation run, you see that there's like a little clock hand on that circle. And that is basically changing the color. So the color tells you the phase, and basically the time of the little circle is telling you your phase as well. Now I can make a superposition state by grabbing, notice that that's spiraling faster in time because that's higher energy. So when we think about our phase changing, it's going to change with energy. And now we see a superposition in position and a superposition in momentum. Now, I can make a superposition that has a smaller coefficient by basically dragging. So it's a little bit difficult to actually interact with this and make your bunch of different superpositions, but there you go, different phases, different coefficients. So we've made a big messy superposition. Cool. Let's stop and actually go through and look at this. So the probability distributions in position and momentum, if we look at an energy eigenstate, they really have the same shape. And that's key, that it is not always true that our position and our momentum distributions have the same shape. And one example of that is when we think about our free particle, a plane wave, which is spread out all in space, is a delta function in momentum. A delta function in position, so a particle that you really know where it is, basically requires a superposition of all momentum states. Here we see the same shape though. It's higher probability on the edges, and that actually means that you have a larger contribution from higher momentums. That's what's going on here. Again, probability distribution. If we watch it change in time, you see that the phase changes, but not the overall shape. And that should make sense since the shape of our wave function is just evolving in phase and time. The overall shape is staying the same, so we would expect our momentum states to stay the same. Now, let's create a superposition of 2 consecutive energies, and then let's watch what's happening in time. So I'm going to do this, and again, we can create, notice as all I'm doing here is changing the phase, you see that in fact changing that relative phase between the 2 states changes what our position and momentum distribution looks like. So I'm just going to pick some phase, and we're now going to watch this evolve in time. And let's slow that way down. Okay, so again, the color is the phase. Don't necessarily focus on that. So I know there's lots of pretty colors, don't worry about that. Let's instead watch how they evolve in time And we did this back with the FET as well, that we created a superposition of two consecutive energy eigenstates, which is what I'm showing here, right? And you can see up here that there's that red line showing you basically the average energy, right? So we've created a superposition of this one and that one, so your average energy is the one in between. Notice this red line is giving you your expectation value of position. So this does actually correspond to something that looks like it's going back and forth in our well. Cool. Notice this red line is our expectation value of momentum. And watch those two lines. So keep in mind that here in this is roughly, let's see, this is roughly my center, right? It's a little bit difficult to not just have that wave function show up, but that's my center. So when my momentum expectation value is crossing where my mouse is right now, that corresponds to 0 expectation value of momentum. That's happening with when the red line in position space is reaching the extreme value, i.e. stopping and turning around. The red line of momentum reaches the extreme value when the red line for position is actually in the center. And so this exactly matches our classical model where you have your fastest speed, so greatest value of momentum, when the particle is in fact in its central position. That's when it's going fastest, and it stops and turns around at the edges. So when we create a superposition of two energy states, we actually see a behavior that looks like it agrees fairly well with the classical model. So that's kind of interesting. And again, just noticing that it's difficult to see that relationship if you only look at the distribution. And so one of the nice things about this simulation is that you can see this expectation value of position, so in the center, turning around, and that expectation value of momentum. Okay, so is this a coherent state? No, it's not a coherent state. We see that the shape is changing. Again, it is periodic. It does kind of repeat the same behavior just over and over and over again, but this is not a coherent state. What's happening in time, the shape of our wave function is very much changing. So this is a superposition. It is not a coherent state. So now we need to follow the instructions carefully to make sure that we're all seeing the same thing. So we're going to click the ground state button, and now I'm going to change and go to translate function. So this is important. It needs to say translate function. And now I'm going to drag this to the right. So now watch what's happening to my momentum distribution. This is interesting. My momentum distribution isn't changing in distribution, but the phase of it is changing. And all I'm doing is changing my initial position, and notice that that red line showing kind of your expectation value of energy is increasing. So the further I start at my position of my wave packet, I'll call that now, but it was just translating the ground state, it's higher energy. And that's like taking our ball that was initially at the bottom of the well and pulling it up the well. So again, to make a semi-classical model, we can think of this as kind of giving it potential energy. Again, in a quantum mechanics way, that isn't what we would say. And we see lots of weird phase stuff happening. Now down here, you see that we've created a superposition state of a whole lot of these basis factors, right? We have many states contributing to this superposition state. So now let's let it play. What's happening? So we see that our wave packet here is moving back and forth, and we see that our momentum distribution is also moving back and forth. So what's interesting here is that this has the same behavior in terms of what's happening with our expectation value of momentum and our expectation value of position as before. That your momentum is basically 0 when your wave packet is getting to an extreme position, and your momentum is fastest, your momentum distribution is the furthest from 0, when your particle is crossing through that 0, this 0 point here. So when your particle is getting to this middle value, that's when your momentum is in fact fastest. So is this a coherent state? Yes. This is what a coherent state looks like. Even though our wave packet here, this Gaussian, is going back and forth in time, its shape is not changing at all. And notice that in momentum, the shape is also not changing at all. So this is a superposition state. We can see that down here very clearly, but this is that very special coherent state. So I'm going to pause here, and in the next video, we'll look at the rest of these.